Hi students, welcome back. Today we are going to solve the linked list cycle problem. This problem is going to teach us a nice little trick on finding a cycle. So let's head to the problem statement first. Problem statement says, given the head of the linked list, determine if the linked list has a cycle in it. So we are given head of a linked list, we have to determine if the cycle has a linked list in it. If the linked list has a cycle in it. So how is a cycle defined? There is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer, which in a way means we can never reach end of the list or null. There is nothing like that. We will always keep going in a loop in the linked list. So we have to return true if there is such a cycle and false otherwise. Let's look at an example. So this example has linked list as shown in this figure 3, 2, 0 and 4. Okay. Whereas the next pointer of 4 again connects to 2 here, which means this 2, 0 and 4 form a cycle, which is why this is a cyclic linked list. Okay. Now if we look at the next example, here again there are two nodes. One's next pointer points to 2, 2's next pointer again points to 1, which is again forms a cycle. Hence, this is also a cyclic linked list. Now, if we look at another example, this is a simple single node list. The next pointer of this will be null. So, we have reached the end of the list. There is no cycle here. Hence, there is no cycle in this linked list. So, let's try solving this problem. So, let's say we are given a list like this in which the next pointer of 1 points to 2, 2's next pointer to 3, 3's next to 4, 4's next to 5 and 5's next to 3. So, one obvious way of solving it is keeping track of the visited nodes. And if we see the same visited node again, it means there is a cycle. For example, let's say we are at 1. Let's say that we keep the list of visited nodes in a queue. We are at 1. We keep 1 in this. When we are at 2, we check if 2 already exists here. 2 doesn't. So we add 2. When we are at 3, again 3 doesn't exist. We add 3. When we are at 4, 4 doesn't exist. We add 4. When we are at 5, we add 5. 5's next points to 3. Now when we are at this 3 again, when we check the visited nodes, we see that 3 already exists here, which means there is a cycle. So this is one way of solving it, but this is not very optimal. Let's look at another optimal solution. This algorithm is called Floyd's algorithm or the Hare and Tortoise algorithm. So like the algorithm says, what we do here is we take two pointers. One is called a slow pointer and one is called a fast pointer. So the fast pointer moves two steps ahead always. So if the current position is x, it always goes to x plus 2. Whereas slow pointer moves only to the next node. It just goes to the current position plus 1. So when we take two such pointers, what the algorithm says is, if there is a circle, at some point these two nodes will meet each other. That means at some point slow will be equal to fast. If such a case exists, that means there is a cycle in this linked list. So think of this like two players running on a circular track. One is going very fast and one is going slow. So at some point the faster player will overtake the slower player. That is how this algorithm is working. Ignore these things because it is not in the loop, but in this circle, once these two pointers start and go at a certain speed, they will always, the faster one and the slower one will always meet at some point. So let's see with an example. Let's say when we start, the slow pointer is represented down and fast pointer is represented here. So when we start, both are at this position. So in the next iteration, slow will go here, whereas fast will go here. Okay. In the next iteration, slow will move here, fast will go plus 2. So fast will come here. Okay, in the next iteration, so these two enter the cycle now. In the next iteration, slow will go here and fast will go to next dot next. X plus 2, right? 5 plus 1 plus 1. So fast will come here again. So at this point, slow and fast are on the same node 4, which means there is a cycle. So you take two pointers, one going to x plus 1 and the other one is a fast pointer going x plus 2. So until you reach the end of the list, if you check if slow is equal to fast at any point, then there is a cycle. If such a point doesn't exist and you have reached the end of the list, that means there is no cycle. Okay, let's see another example. Let's say this time we are given a linked list without a cycle. Now our slow pointer is here and our fast pointer is here. When we go to next, our slow pointer will come here and fast will go here. When we go to the next iteration, slow will go here and fast will go here. In the next iteration, slow will come here, but for fast there is nothing else. It has reached the end of the list. That means there is no cycle. Since the end of the list is reached, there is no cycle. Oh, there is no cycle. Okay. Okay, let's write code for this. So the algorithm is pretty simple. Okay, let's take two pointers. So here we are given the definition of the linked list node. Each list node has a value and has a next pointer. We are given head of such a node. So that means in this example we are given a pointer to 3. Okay. Now let's take, according to our algorithm, let's take slow as head and fast also as head. Initially both are starting at the same position. So while slow not equal to null and fast not equal to null, okay, what do? Slow goes x plus 1, which is slow dot next. Fast goes x plus 2, which is next dot next. Okay, and at any point if slow is equal to fast, then we return true. Okay, now if no such thing exists and we have reached the end of the list either with slow or fast, that means there is no cycle and we return false. Okay, now another thing we have to observe here is, will there be any null pointers? Slow, we have checked that slow is not equal to null, so slow dot next will not return null. We have checked fast is not equal to null, so fast dot next will not return null. But we are also doing fast dot next. So we also have to check if fast dot next is not equal to null. Okay, otherwise when we reach the end of the list, fast dot next is null means it might throw a null pointer exception. Okay, let's run this solution and see. Yeah, let's submit it. Yeah, it is accepted. So what is the time complexity of this solution? We are just traversing this list once. We are using two pointers, but we are going only one sweep. So it is order of n. What is the space complexity? Except for two pointers, we are not using any additional space. So it is order of 1. Yeah. Hope you have enjoyed this problem. So do try it out on your own and keep improving your problem solving skills. Happy coding. See you in the next video.